Okay, so my name is Andrew Kent, and I'm going to talk about our paper, Occurrence Typing Modulo Theories, which is some work I did with David Kempe and Sam Tobenhockstadt at Indiana University. And this is kind of a cute name for basically taking typed racket and adding refinement types in a way where the theory is modular, that you're refining with. And so diving into some examples, let's say we're looking at a vector of Stooges, right? And the type that typed racket today might give you to describe this value would be something like vector of string. And so that certainly tells that it's not like the clearest picture you might be able to have. Bracket, we can kind of enrich and clarify that length is equal to 3 with that refined typed racket today. If you made them, a little off by one error, type for vector reference, which just says the index has to be running of your program at some point. And a vector access, and this where here is just a simple refinement that I showed you earlier. And with this between 0 and the length of the vector, so we get warned about that as we build our program. Is this great? And this allows you to do things. And a thing about looking at vector, for example, is they're all over the place. About adding refinement types to typed racket, and then later vector accesses and refinement types and some reasons logically about racket, mathematic racket, and the difference ref when we were looking at or a vector. There's a little, type theory check programs. We know that X is a list or a vector. And well typed, nothing really interesting there. Value from this test, we actually learned something. And so we call this the then proposition. If it's not true, it's false, and in that case, we learn that two propositions are the things you get to assume in their respective. Looking in the then branch here, X is sure enough, that's what we get to assume because of how we type checked the. A little more complicated. For X's there, we started out as a list or a vector, and we now know we can derive that X is in fact a vector, and the insight here is that the way that typed racket works today, conditionals expose. In adding refinement types, use these propositions that are already being generated. So if we were to look at a model, how we might extend this, so you have expression, natural thing that is a part of how typed racket works. For type checking a language, that's actually what the type environment. Now we look at that type, and in order to extend in adding, the types to include a type that uses. Now, it's a little more. Just have these propositions you see here or are not of a type and do logical. And so if we look at structured, internally there's subtyping and the typing judgments for different links. Logic, the ands and the ors that are in the done is added a way to kind of solver find your types with. And it's key. So if you want to do linear arithmetic, those propositions are going to be we worked with as well. Something you could do. So what we've done, and this is kind of modular with the theory that you would like to use for point, looking at this list of X tests as a dependently typed language, and it's probably not. Output of the type checking process, we had some terms to clarify what's going on. So what term dependent type if we're looking at function application, for example? Function is a function type, and that the argument, right? And then when you're taking the type of that application, you substitute in for x, which is the domain of the function, that term that you called it on. And so that's how you can get some dependencies on the things you're calling this on. But in Racket, we want this to work in as many Racket programs as we can. You can have some pretty problematic terms that appear there, right? You can have mutation, you could have interacting with I/O, I mean all kinds of stuff that you wouldn't want to just lift up into your logic and try to reason about as some pure mathematical thing. And so typed Racket, instead of doing that, it does another analysis on the terms, and it generates what are called symbolic objects. These are like the whitelist of things that are allowed to be lifted to the type level. And so when we're looking at what those things are, so the null object basically says this term cannot be lifted into types, or there's not anything interesting there. You can lift variables. We want to be able to reason about those in our types. Field accesses into objects, so you can reason structurally about large pieces of data that are built up. And so that's what in typed Racket we use to substitute in for that the argument of the function there. And in adding refinement types, we needed to do a little more. Basically, we needed to extend objects, and depending on the theory you're working in, you're going to want some more terms that are relevant to that theory appearing there. So for the vector example, we want to reason about the length of vectors in a more specific way than typed Racket needs to today, and we want to reason about linear combinations of these symbolic objects. And so walking through an example, here we're testing that the first of p, if it's a byte or not. And so in type checking this, we check that byte, yep, it's a function type, compatible type, let's say. And when we're looking at the return result, tau there, we observe, okay, that field access into p, it has a symbolic object of first of p. And so tau, whatever type it is, in the general case, it can have occurrences of x in it. In this case, propositions, saying you can learn it is or is not a byte. And so when we do the substitution, those just kind of naturally flow in there, and you get the information that you would expect from applying it to that argument. Now, looking at a slightly more complicated example, we can see what we had to add to make this work with our refinement types. So here, we're testing if I is less than some byte that we read in from maybe a file. And this is just to emphasize a term there that we don't want to appear in our type theory. So we check kind of the standard stuff that you would expect, and then as we get to these symbolic objects, you see that read byte has a null symbolic object. We don't want to pull that I/O operation into the type theory. And so in looking at tau, the return result, we have these are the things you learn if we test on that. Doing the first substitution, the first argument for I, just simple as expected. But the second substitution, where the object is null, today, typed racket, it just kind of says, okay, propositions that we're talking about that we need to forget about at this point and just keep the things around that we want to reason about. And this wasn't expressive enough for us in practice. You'll see that if, for instance, read byte, we know that y is a byte. And so if we just forget that information, we may not realize that although we don't know exactly what I is less than, we know it's less than some byte, and so that gives us an upper bound for I, for example. And so to deal with this and keep some of this information around, we took kind of the standard approach from logic, and that's using an existential quantifier. So we say that, look, there's some y, we don't know exactly what it was or what program term it relates to anymore, but it was a byte, and then we can have that information kept around. This notion of using existentials is an idea that was laid out in great detail and is used in even more areas in this really interesting paper by Knowles and Flanagan. So it's really well written. I would recommend reading that if you're interested in that approach. Our key difference, I think, is that we use this approach for that null object case where we don't want to lift things, but in the other cases, we're happy to do the substitution and go ahead and do the standard thing. Now, as I mentioned, because we added this and kind of looked at vector accesses as a case study that is widely available, we were able to do an evaluation to see how well it worked. So we looked at the Racket math library, and you can use that from typed or untyped code in Racket today, but internally it's implemented with typed Racket. And it has about 22,000 lines of code, and vector references appear all over the place in there. And so if we think about kind of how maybe vector reference could be implemented here, you have the kind of simple type that it takes a vector and some natural and then gives you back an element. And when you call it, it does a runtime check to make sure that that index I is less than length. And if it is, it does the raw unsafe memory access. And if not, it throws some kind of an error. And so we were able to look in something like the math library that has vector accesses and different modules all over the place and kind of get a feel for, so they're using this standard vector access right now. If we enrich that type and make it so that they have to be able to prove that the in there is a valid index, what's going to happen? Are some clients going to be fine and others are going to be able to not satisfy that in a reasonable way in their program? And so what we ended up doing is kind of creating two interfaces in our evaluation. So the safe vecref is the one that requires that static guarantee to be provable, and then it can just do the direct vector access. And then we left the old interface in there, the vector reference, so that in programs where that just made more sense to use, they can use that kind of lower barrier to entry on the type for that. And that means that some clients can use that simpler one and type check just fine as they were, and others can type check using the more specific one. So that we kind of noticed that there were some primary categories where we were able to use these verified vector reads and writes throughout these libraries. And so the first one I want to talk about is those where we didn't really need to make any changes. And to illustrate these, let's talk about kind of a well-understood example. So taking the norm of a vector. So you have some vector in a vector space, and to take its norm, you square all of the elements, and then you add them together, and you take the square root. And so here's the Racket code for that. So we take the vector x in, and then we have those two variables there that we're going to loop with. So I is the index that we're going to be iterating, and res is the result, so the thing we're accumulating. And so in the body of the loop, you do the test, is this still a valid index? And if so, pull that value out, square it, add it to the result, and iterate with the next index. And otherwise, you've kind of run past the end of the array, so just go ahead and take the square root of what you've been accumulating. And in programs like this, where we have this test that's kind of right there as a guard to the vector access, and its then and else propositions are telling us the information we need to know, the safe vector references just kind of out of the box worked. We didn't need to do anything, and that was provably a valid index there. Things that were of this form, where they just kind of worked out of the box, made up about 25% of the vector operations in the math library. The next class of things is kind of, we don't want to make any huge changes, but what if we just added some type annotations to our program? What could we get then? So here again, this is that exact same code we were looking at, taking the norm of a vector. And if we just tweak it slightly, so now you'll notice I is not initialized at 0. We start instead at the end of the vector. And our test then is, well, have we gone negative? Are we beyond the beginning of the vector? And if so, we're done. Otherwise, we're still at a valid index, and so go ahead and do the operations in the loop. And in cases like this, out of the box, putting that safe vector access in there, the type system was not able to verify that using just the simple standard type methods that we put on there. And the reason is, kind of as a human looking at this, we look at I and we see, okay, during this loop, I is actually only going to be between -1 and 1 length of that vector length. But reasoning like this just isn't apparent with the surface level types that are sitting there. But fortunately for programs that kind of fell into this class, by adding just a simple refinement, in this case, saying, look, yeah, that's an integer, but it's always going to be bounded by that initial value that it's given, we were able to make programs like this type check. And so for programs where simple annotations and just kind of making more explicit the invariants that were there in the program, we were able to get the number of verified vector operations up to about 59%. And for the last portion that we were looking at, we wanted to see, okay, we don't want to completely rewrite the math library, but are there a class of these programs that we can make small changes to and get kind of a obvious bang for our buck here in removing checks and doing vector verified operations. So for this, we can just look at a nice simple example taking the dot product of a vector. So here's a bracket implementation of that. Same structure as the norm we were looking at, right? We have this recursive loop. We're iterating the I index over these vectors A and B. And we do that test on A, which is kind of the exact same test we saw before. And when that fails, then we are done. And so in cases like this, something interesting popped up, and that was we kind of had some of the information we needed. So we knew that the A access was valid, but the B access we couldn't verify. And you'll notice there's no test in here about anything about V. And that's because for this particular function dot product, with the way the types are written now, there's kind of this implicit assumption that the people calling it are going to pass in vectors of equal length. And so you kind of have two options in this case. You can you can add, this refinement to the type of dot product, but then you can have kind of varying success with this. You may find that that works for everybody, but you may find that for some functions, in the places that it's used in something like the math library, it's difficult for some clients to consistently prove those things with the types. And so in cases like that, sometimes it made more sense to, instead of just changing the type of the function, to instead leave the type at that simpler description and instead just kind of put a check in there. So here at the beginning now, we're testing, okay, is A and B actually of equal length? And once we know that, the loop testing on A is enough to verify that these vector accesses are going to be provably safe for both A and B. Adding the ones that we could verify with this brought us up to about 72% of the vector operations in the math library. We could prove that the bounds were indeed valid. And so in total, we looked at the math library, and that was one by far we spent the most time examining. We also looked at the plot library, which is actually the tool I've been using to build these graphs that you've seen so far, and the Pict3D library, which is a pretty cool functional interface to the OpenGL rendering software. And so in total, we were able to look at about 56,000 lines of typed racket code. And in our paper, we go into detail about the results. But as you can see, we had kind of varying levels of success. But overall, we were able to do quite well when you look at how much time we were spending and the things we were able to verify. So in our paper, we go into depth on the formalism that we use to do this analysis and our proof of soundness. We, in our artifact, have a REDX model that we used in designing this. That's kind of a small toy version that you can run and look at the details of how that's working. And we also, in our artifact, tried to make it really explicit and easy to see for the math library that we spent a lot of time working in, what changes were necessary to get those vector operations safe. So you can look at all the gory details there and see what things we changed, annotated, added, and all of that in the artifact. So this work that I did was on a fork of typed racket and was a great learning experience. And shortly, I will be merging these changes and features into typed racket. So that's something that soon you'll be able to download in a racket release. And that's all I've got. Thank you so much for listening.
Hi, I'm Arjun from UMass Amherst. So this is really cool work. I really like the story of sort of integrating the type system with an arbitrary solver. But another older part of the type racket story is that it's a gradually typed language, right? And so these types sort of get translated into contracts and so on and so forth. I know you know what I'm talking about. So I'm curious whether these two stories work together. Like, is there a way to do you have a gradual typing story too?
Yeah, so the short answer is that was work that we didn't get to implementing and evaluating. But if any theory where you could articulate those propositions and translate those into contracts, it should be a trivial extension to make those things that you can enforce. So if all of those propositions that you're looking at are things where you could imagine a simple dynamic check verifying, we would imagine that you should be able to check that, but we didn't get to implementing that in our work.
Yeah, if I could just ask a follow-up question on that. So one of the things that I was surprised when you gave your little example of the small modifications, and you had the quality of the lengths of the two arrays, I was really expecting to see that appear as a contract in that method, but that's not how you chose to implement that. And then having information from the contract flow into the assertions that you need to discharge in your typing story. So is that future work you're going to get to, or?
So that's a great question. There's some folks at Northeastern who have been doing some awesome work in making typed racket and the really rich and well run through the ringer contract system actually work together, so you can start to use those. And so I imagine, I don't know if they're done with that or if they're nearing completion, but shortly we should be able to start integrating explicitly contracts, which is kind of what you would expect in things like that, and types, and be able to do that, absolutely.
It's a more technical question, which is, so you spend a bit of time explaining why, in the function application rule, you don't want the random E2 to show up. By random, I mean some arbitrary E2 to show up in the output refinement. Sam knows what question I'm going to ask right now. So one of we have a rather simple hack that gets around that, which is you just convert the program to ANF, and so all applications, just the E2 is always just a symbol, N. And so then now you use the function application rule, you're just substituting binders for the input parameter of the function with
Sure.
N. So why does that not work in your setting? There must be something I'm missing.
Well, so
No, you go.
yeah, I'm not sure that wouldn't work, but the kind of design philosophy between typed racket, and Sam can interrupt me since he's the initial creator of it, Typed racket doesn't do much translation of your program at all. So it does all of that checking and verification, but then the program that you get out at the end is almost exactly the program that you wrote. So rewriting it and reasoning it about in that way could be another effective way that gets similar, if not the same results, I would imagine. But that's just not really how typed racket, at least right now, is geared to work with racket programs.
I could just say one other thing along those lines, is that I think you have to make those same choices, even if you go to ANF, you then have to make those same choices about which qualities do you get. You have some variable, or variable is equal to the output of some IO function, and you don't want to represent that in the refinement. If it's equal to some structure access, then you do it. We're making the same choices there that Andrew talked about. The one other thing I was going to add is, so at some point you have to substitute concrete values for those binders. And you have to decide what space of concrete values you're interested in reasoning about. So I don't know how you deal with that in the refinement types, but it seems like on that one slide you're making a certain choice of the space of values that you will substitute variables. And so actually I was a bit surprised on that one slide that you admit any variable with any type, as opposed to, I don't know, maybe some subset of types that correspond to values that are within that space that you can reason about. Because I was worried about how you would improve the substitution line. But maybe that's too much of a question for our audience to tell me afterwards.
Yeah, so we could get into some technical details about the proof of correctness. You mentioned any variable, so there's a small caveat I didn't mention, which is mutation is a thing you can use in Racket, although it's maybe not the thing that everybody does. And so we do a really quick preliminary scan, and variables that are mutated, we don't reason directly about those in the theory. So we do a little bit of, yeah, I don't know if that was, but yeah.
Hi, very interesting work. So just a small question. In your norm example, you reversed the order of iteration to be backward, to be able to type it. Is there a real problem in doing it forward, or is it too easier for this?
Are you saying, excuse me, are you asking if there was a real program that kind of did that backwards iteration thing?
No, is it a theoretical program to do it forward, or is it just there is a way to check it for forward iteration?
Is there a way to check it for forward iteration?
Yeah.
That was the first example, I believe, if I'm understanding your question right. So those programs were identical except for the order that the index was operated. And the first one worked really just easily. It just naturally worked.